We're going to look at this first part here. At time t equals 2, the train's position is 300 meters east, and it's moving east. Write an expression involving an integral that gives the position of train A. So this position then will be equal to our starting position of 300 meters. Since we're moving to the east, we can think about this as west to east. Then we are going to add the integral of our velocity of train A dt, and we're going to go from 0 to 12. And they've told us they want us to use a trapezoid sum with 3 integrals. So that means I'm going to kind of box out our integrals here from our table. This first one's going to be our first trapezoid. Then in blue, I've already found an error. We're going from 2 to 12 because they gave us an initial position at 2. So we're looking from 2 to 5, and then from 5 to 8, and then from 8 to 12. So our trapezoid will be 300 plus, we're going to go from 0 to 100, average that out, and multiply by our base. Oh, I've made the same mistake again. We're going to go from 100 to 40. Average that out. And then we're going to have a base from 2 to 5 is 3. Then our next section will be 40 plus a negative 120. Find that average. From 5 to 8 is another base of 3. Plus negative 120 plus a negative 150. Find that average. And that base is 12 to 8, or 4 is our base. So as we add all of this up, our position is negative 150 meters, or 150 meters west of the origin station. Not a related rate problem, but a good trapezoid and integral of velocity for position review. As we think about the second part here in blue, now they've given us a second train, train B, that appears to be traveling to the north. And again, train A was traveling to the east at this time t equals 2. So as we remind ourselves, train A has an initial position of 300 meters east. That was given in the previous part. And we also know that at that instant of t equals 2, train A has a velocity of 100 meters per minute. We can think of that as the dx dt, the change in the x direction. Then they tell us train B has this velocity, and at time t equals 2, its position is 400 meters north of the station. So we're talking about here, we are 400, and our velocity is given by this equation 5t squared plus 60t plus 25. Find the rate in meters per minute that the distance between train A and B is changing. And so here, if we look at this, this is part of a triangle, and this hypotenuse is the distance between the two trains. So now we finally have to come up with a base equation. Our base equation is the square root of a squared plus b squared, or we'll go ahead and use x squared plus y squared just because that's kind of how we've got this going so far. Or maybe even easier, instead of using the square root, we'll say L squared equals x squared plus y squared. And so they want the rate that the distance between the two trains is changing. They're really looking for what is dl dt. And so in order to find that, we are going to differentiate this entire equation with respect to t, and we'll get 2L dl dt equals 2x dx dt plus 2y times dy dt. If I were to divide everything by 2, the 2's would get cleaned up. And so then as we look at substituting everything we know, this L can be found using our two initial positions. That means our initial L will be 500. The dl dt is the quantity that I want, the rate I want. X started at 300, and its rate was 100 meters per minute, plus y started at 400, and that dy dt we don't know yet, but it can be found from this equation. So all we're going to do is plug in 2 everywhere we have a t. When we run that calculation, we get 245 meters per minute. So that'll go here, 245. And now dl dt is the only thing we don't know. After some calculations, you'll find that dl dt is equal to 256, also meters per minute. Makes sense that this is a positive quantity because this length is increasing, and it's increasing because both B and A are moving away from each other. In this case, we had to come up with our base equation. All of the other problems before this point had a base equation given.